concentration. Every 6 kilojoules per mole of delta G is about 1 order, it's a bad one, it looks like an L, 1 order of magnitude in concentration. So let's make a little table here of a delta G versus our Q or KEQ, whatever. If it's 0, it's going to be 0. Okay, that's kind of pointless. If it's 6, let's say negative. Let's talk about favorable things. Because favorable products are bigger than reactants, right? It's going to be 10, sorry, if it's 0, it's going to be 1. Oh, God. Lynn, I know how you work. If it's 6, there's going to be 1 order of magnitude more product than reactant. Another way of writing that is 10 to the 1. Another way of writing this is 10 to the 0. Negative 12 is going to be 100 to 1, which is 10 to the 2. Negative 18 is going to be 1,000 to 1, 10 to the 3. And we just saw negative 30, right? That was a problem just a little while ago, was like 1,000,000 to 1. 10,000, yeah. Right? Every 6 kilojoules of energy is an order of magnitude, a power of 10 on products and reactants. We could go the other way too. If I have a delta G versus my KEQ, whatever, now I'll do it in that way. If I have positive 6, my KEQ must be 1 over 10, or 10 to the negative 1. Positive 12, 1 over 100, or 10 to the negative 2. Positive 18, 1 over 1,000, 10 to the negative 3, etc. Every 6 kilojoules of energy is an order of magnitude. That's really helpful for me for placing, like, what are we really talking about? Because we learn in biology class things like ATP falling apart into ADP plus PI has a delta G of like negative 30 kilojoules per mole. Is negative 30 big? Is it small? 30 sounds small to me when I think about a bank account, right? Like I need some context. But using this rule of thumb, I say that's 5 6s, right? It's 5 6s. So it's going to be like, well, I messed that up, but 5 6s, it's going to be like 10 to the 5th to 1, right? 5 6s. It's going to have a whole bunch of product and very, very, very little reactant. If this reaction's going on, I'm going to have a lot of ADP and PI and very, very little ATP. It's huge. And that's another good way to keep your mind in order. This is huge. The reason our cells use ATP is it's one of the highest energy reactions we can do in the body. So if you want to calibrate your like speedometer, 30 is like maxing it out. Negative 30 is like, holy shoot. That's a really high energy reaction. And I think it's something we take for granted a lot in how dangerous things around the house can be and whatnot. A good example, I think, is a car battery. If I convert the units, it's a 12-volt battery. If I convert car battery units to kilojoules per mole of lead acid electrode, whatever, a car battery is like negative 2,000. There's a reason it hurts you to electrocute yourself on a car battery. The biggest reactions we do in our body are like negative 30 is really good. And like a car battery is like negative 2,000. It also shows why we're not good at making cars go at 60 miles per hour with our little leggies. Run like the Flintstones, yabba dabba doo, run. We only get 30 kilojoules per mole from our best energy reaction. That cannot compare to the thousands of kilojoules per mole of burning fossil fuels, or if you have an electric car, of that battery voltage interaction. There's a reason humans don't run 60 miles an hour. We don't have the chemical reactions to do that. We need new reactions. And power thirst drink. I don't know. Red Bull, right? Okay, so I want to take this one step further. And what I want to show you is here, I'm talking about standard energies and equilibriums. But ultimately, I usually don't really care about equilibrium. I want to know what's happening inside a cell. That's what matters to biochemists usually. So I'm going to take this same example and extend it. And I'm going to say you looked this up, because you could. This is not me making these numbers up. This is from one of those books. So you find for this reaction, it has a KEQ of 1.97, which you can also express as a delta G. I don't know why I keep dropping the prime, of negative 1.681 kilojoules per mole. And then I tell you, in the actual reaction you do, you don't use 1 molar of them. Why? You use this. You add 1.5 molar of this and 0.5 molar of that. What's the driving force in that? Will the reaction in those conditions still be spontaneous, or will it not be spontaneous? Where is it going? And hopefully I pointed loudly and long enough that you're going to be using this guy. I want to know what's actually happening. I need to know my standard energy, and I need to know what my actual concentrations when I start the reaction are. So see if you can figure that one out. Chat to your neighbor. Make sure it makes sense. And if it doesn't, we're doomed.
Tonight at 11.
What?
Tonight at 11.
Tonight at 11. Doom! Oh, Morbo. Yeah, 280 is generic protein. It's tryptophan, whatever. And 489 is the fluorescence of GFP. Cool. And you can find a molar extinction coefficient for it somewhere, so you can use Beer's law.
Oh, yeah. That's what
Yeah. All right, we're not clicking in. So are we lost or just working?
Working.
Working, okay. We'll give ourselves a minute.
Careful of which is product from China. Otherwise, it's 1/3, right?
I know.
Okay, cool. I'm just going to look at it. Oh, there we go. Did it right there. And then I just never looked back. Oh, right. Yeah. Oh, no, no. You as a negative? No, what's it? Then I go.
So would that just change on to
That would change if that's negative, correct?
That's only this.
Yep, I got that.
This one is why we're
Really?
Yeah, all I did was
You don't look like
sign
you.
in there. I was like,
It's been 3 years and I can tap on it. Yes.
All right. We have largely clicked in. And I want to show where we're ending up. Keep working if you're working, don't worry. So we're ending up with most people at D, but a significant fraction at A. And if you got either A or D, I want to tell you you're on the right track. I'll ignore the B and C for now. To get either A or D, you have to set it up mostly correct. The correct answer is D. Let's get that out of there. And where we're happening to get A is from being sloppy with which one of these is a product and which one of these is a reactant, and where those go. So what we should be getting at is that delta G equals negative 1.681 kilojoules per mole, plus RT, which is about 2.5 kilojoules per mole, RT, times the natural log of our concentrations we started with, which is products over reactants, and is thus 0.5 molar over 1.5 molar. If you flip those, you get A. But the correct one is this way. And that leads to D. Okay, let's talk building a chemical intuition. When you start with a 1-to-1 ratio, which is what we mean by our standard stuff, it's favorable towards the product. Now I start in a situation where I've got even more reactant. It's going to be even more favorable. Le Chatelier's principle is going to push that sucker forward. Does that make sense? I said that fast, but it's a good principle to check yourself on. If under the equilibrium, which is 1 molar to 1 molar, it's already favorable, and now you have an abundance of reactant, what happens when you add more reactant? The reaction shifts forward. It becomes even more favorable. And so your delta G actual becomes negative 4.4 kilojoules per mole. Good stuff there? Okay, we've gotten through most of this stuff that we need to think about. I don't know. Stop that. My computer is slowly dying. Sad. Sad day. Wah, wah. So again, we've started to work through some of these problems. How do I apply these equations? And we're going to do more. We'll do more on Monday. This takes time to soak in, to get how the problems are phrased and what we're looking for into your system. And we'll probably do more in a second. But I want to point out another way to look at this. A lot of today is about building a language of communication, right? When I say a reaction's favorable, hey, that enzyme catalyzes a favorable reaction, we need to be on the same page. You need to be saying, how favorable is it? Right? It's not a game show, but we could. We need to have a language. Favorable is just a direction. There's just like charge. It's not negative charge, it's -2. It's not favorable, it's favorable -7, right? We need to build that communication device. Here's another way we could look at it. A reaction in this kind of fun reaction coordinate diagram, I like to harp on these about how much I hate them, to point to me a coordinate. I don't know what that means. It does not mean time. It does not mean concentration. I don't know what it means, but they're used all the time. I'll just roll with it. We have some initial state, our reactants, that are at some energy level. What does it mean to be at some energy level? Some delta or some G naught? They have a certain bond and structure arrangement and at a certain concentration. Right? We said that delta G comes from structure and concentration. My reactants are of some structure at some concentration. And we have products, which are at different structures and different concentrations. And the difference in energy between those is our delta G, the delta of the change in that concentration and structure. And I want to point that out to really harp on the fact delta G is asking a different question than the activation energy. This hump up here is what we call the activation energy, and that's an entirely different kettle of fish. The delta G of the reaction is the free energy of the difference between the reactant and products. Tells us whether the reaction will proceed spontaneously, whereas the activation energy is how much energy is needed to initiate it, and it tells us the rate of the reaction. A good example to put this in context. Again, we're trying to build a language. We're getting some examples. Hopefully it's sticking. If not, you can beat me up on Rate Your Professor or whatever. Is a good example of this might be diamond turning into graphite. The delta G of diamond turning into graphite is negative. It is a spontaneous process. That tells us the direction the reaction will go. The activation energy for this reaction is huge, which means the rate is very slow, which means don't worry if you're wearing a diamond ring, it's not going to fall apart on you. It might in a few million years. But it is spontaneous. If you leave diamond alone, if we shoot a diamond out on a spacecraft traveling the stars, that diamond will eventually turn to dust. It'll take millions and millions of years, but it will. It is spontaneous. It's just really slow. Another good example of that is our DNA falling apart. DNA, as a big structure, losing the phosphodiester bonds and falling apart into individual nucleotides is spontaneous. It also has a very high activation energy, thank goodness, so that you don't feel your DNA falling apart constantly. But it will, which is why we don't have dino DNA lying around. It is favorable for the DNA to fall apart, and that's a thing that will happen. And so we have to kind of get those two terms in our mind, that spontaneous or favorable is a completely, I can't even do perpendicular, there we go, words, a completely perpendicular axis to fast or slow. You can have a spontaneous fast process, you can have a spontaneous really slow process. You can have a non-spontaneous fast, you can have, they're different axes, they're measuring different things. And all this equation stuff doesn't tell us a thing about rate. It only tells us about spontaneity. We're going to talk about rate later. That's going to be a whole big kit and caboodle, but it's a different question, and it's a different thing to explore. Yeah, Leah.
If you have a spontaneous reaction going towards the products, when you reverse the reaction, will it always require energy to reverse it, or are there some cases where both ways can be spontaneous?
That's a great question. We're actually going to get into that a little with enzymes, but let me give you an analogy, because I think this is a great question Marleo raises. If A going to B has a delta G naught prime of like -3, typically we would say then B going to A, sorry, let me not cloud this up. We would say that B going to A would have an equal and opposite. It would always be +3. And the laws of thermodynamics tell us that that's going to work. But in the body, structures are complex enough and there's ways to get at things that what if instead of going B to A, I went B to C to A? This pathway could still be negative. So you could get from B to A still in a favorable way, but not directly. You would have to take a different route. I like to think of this like skiing. It's easy to go down the slope. If you asked me to trudge up the slope in my skis, that's really high energy. That's hard to do. So I don't. I take a ski lift. I take a different path. Right? And that's easy. I just sit on my butt. So as long as you have a different chemical path, you can get there. And that actually ties into a little what we're going to talk about right now. I swear I didn't plant her.
5 bucks, please.
Oh, damn. Here's a good example of that exact principle, which is glucose combining with phosphate to form this molecule glucose 6-phosphate is unfavorable. Glucose is quite favorable by itself. Glucose with a phosphate on it is less stable. It's hard to do. It's a positive delta G. It's unfavorable, non-spontaneous. ATP falling apart into ADP and PI